I would like to give a warm welcome to Dr. David DiVincenzo. David DiVincenzo is the director of the Institute of Theoretical Nanoelectronics at the Peter Grunberg Institute in Jülich in Germany, professor at RWTH Aachen, Germany, professor at TU Delft, Netherlands, and staff member at QTech in the Netherlands. Many of you know his name from the DiVincenzo criteria, the necessary criteria for a quantum computer that have made great impact on the quantum computers being realized right now. He also proposed the first spin qubit quantum computer, the Los DiVincenzo quantum computer. And about all of this, you will learn a lot more today. David DiVincenzo did a postdoc at Cornell and then was a staff member at IBM for a long time until being called to Germany and becoming a director and professor there. We have the Discord open for all of your questions. David will give a lecture first, and then we will do a long Q&A session. And we are very excited for all of your questions being asked to David. David, thank you very much for being here, and we are ready to kick it off.
Okay, dank u wel, Marlou. And can you see my screen?
You can, yes.
That's very good. So I will launch right into a lecture today on quantum computing. I think that you, those of you in the audience, represent a great diversity of backgrounds. So I'm going to also hit a diversity of topics. So here's my outline for today, but I will leave plenty of time for discussion at the end. I will begin with what I consider the most essential thing to know about what is a qubit and how it is distinguished from a bit. And so that will be a small tutorial about that. And you may wonder, what do I feature as the most important thing about a qubit? Well, you'll see it in a moment. Then I'll jump right to the present and show you maybe my favorite quantum computer of today, which may be a completely different one than the quantum computer of next year, but is worth looking at and trying to understand some of the features that have emerged. For many years, quantum computers were just a dream. And we were often criticized for saying, well, you know, you keep saying it's 20 years from now, and then another 5 years later, you say it's 20 years from now. But now I can say, yes, in fact, we have quantum computers, but we'd like to have better ones. So when will we have a better one? Well, 20 years from now, I guess. But I think they will actually continually get better. I will spend some time digging back into the history of quantum computers, and we'll talk about the start of quantum computing, except I don't know what year to point to, so I'll point to all of them. So here's my list of my favorite years: 1960, or is it 1982, 1994, 2000, 2016. I could say 2016 is the year that IBM put its first quantum computer on the cloud, and maybe for many of you, that's the starting point. That's the one that marked the era of real quantum computers. But for me, or certainly intellectually, the ideas of quantum computers started way further back, and including many high points over the years. And somewhere in there, somewhere in my sort of historical story, I will tell you about those criteria that you heard about, and tell you what I was trying to do when I wrote down those criteria for the first time, which, well, to give you a clue, was sort of started happening already in 1994, and were sort of complete in the year 2000. But they're not maybe the most important aspect of the timeline. Okay, so now I'm going to begin with some really basic stuff. So I'm sure I'll bore some of you, but I hope that it's at least a little bit interesting and a little thought-provoking also for a few of you, even experts. So we talk about computing, and at least for the last 100 years, when we talk computing, we mostly talk about binary arithmetic, and we talk about, therefore, information represented in as one of two states of some object, call it 0 and 1. And now we recognized, although I'll point out it was not even so obvious in the timeline until rather long along the timeline, that the most essential thing that you wanted to do to introduce quantum mechanics into the story of the bit, into the fundamental information carrier of digital information processing, is promote it to an object that from which you can build a wave function. And so that if you have just a single bit, you should be able to make states which are not 0 and not 1, but which are, as we say, superpositions of those two, with some coefficients, some actually complex valued coefficients A and B. So we say that there's a physical reality to saying that a system is in a definite quantum state, but which makes it indefinite from the point of view of whether it's a 0 or a 1. And the point I will make is that with a small sort of Gedanken experiment is that it's not merely that it's sort of unknown whether it's 0 or 1. It's a much more definite state of knowledge than that. So let's do this by imagining that we're representing our physical, let's say, bit of information with whether a single particle, I do say single electron, and this is a qubit that we've thought about over the years, but do not find favorable, does not have really good characteristics, but is conceptually a perfectly good qubit, where we say the 0 and 1 of this single electron is whether it sits in the left side or the right side of a bistable potential well. As I said, there are so-called charge qubits, which still play a little bit of role, but which were long ago displaced by spin qubits as a favored single electron qubit. Okay, so, well, we do have the situation as the digital computer engineer would want it, single electron on the left, 0, single electron on the right, 1. So what about these other states, these alternative states? So the way I describe it here, and it was Deutsch who actually really articulated this very precisely. He says, to get to quantum mechanics, you have to think about first the idea of randomizing, paradoxically. And so you may want to bring the system into a situation where it is neither a 0 nor a 1, but in some sense a 50% 0 and 50% 1. And a regular computer engineer would know what this means also, because if you make a hardware random number generator, you do things exactly like what I'm describing here. That is, you have a bistable system and you put it in a condition where it doesn't know what to do. Or the way I've described it here is suppose you start it in the 0 state, but you do something to make it less definite, which is, for example, to make the barrier lower. And then you would often say, well, you make it so low that even thermal excitations will cause the system to bounce back and forth between 0 and 1. But I won't follow that track very much, but I will just say that for whatever reason, lowering the barrier will give the system some chance of departing from the 0 state and actually ending up in the 1 state. And suppose that probability of doing that is 50%. So you could say, and you do in fact say in a hardware random number generator, that that's a good way of producing a random bit. But from the point of view of quantum mechanics, is this state really random? One might ask. But now we have to indeed discuss more of the physical process that's involved in going from the 0 to the 50-50 case. And what we will say will be more specific here and say that that is going to occur because of tunneling, because of electron tunneling, and therefore because of a purely quantum mechanical phenomenon that particles can indeed penetrate through walls, can pass through regions where they're forbidden to be by the laws of classical physics. And so you can indeed lower the barrier. I show this sort of dotted version of the barrier, lower it enough so that indeed tunneling can occur, and then it can bring itself into this 50-50 state. Now, I see I already jumped into the punchline. I should have stayed on the last slide, because what's really very different about quantum mechanics is that you can prove that this 50-50 state, this apparently random state that you end up with, is actually not at all random. And you do it by performing or continuing the thought experiment in the following way. That is, you lower the barrier once, let it get into this 50-50 state. You raise the barrier again, hold it stationary for a while, then you lower it one more time. You try to make it, quote, even more random. But instead, it sort of completes its quantum tunneling, and it ends up definitely in the one state. So we say this superposition of 0 and 1 is not at all random, because I do something to it which from a classical point of view would make it even more random. But in fact, it makes it actually less random. It sort of completes a process and turns it into a one state. Now, this process of flipping from 0 to 1 is in Boolean logic what you call the not operation. And so what I've described is something which you do twice to get a not operation. And so we refer to this as a square root of not, as a logic operation. And basically this, with ordinary Boolean logic, the ands and the ors of ordinary Boolean logic, is enough to give a whole new type of logic, which is the one based on quantum physics. So I featured this one particle, one bit superposition as the sort of key new feature. You would often say, well, but surely the new feature is entanglement. But I would say this plus ordinary computer logic inevitably gives entanglement, which is just two-bit entanglement, or two-bit superposition states, or more than 2 bits. So once you admit the possibility of having superpositions with this sort of deterministic character, you inevitably bring yourself into the state space of entangled states and into the rich information carrier that quantum states give you, and to the essentially new software that it makes possible, the new instruction set that is made possible, that has, as is very famous, of course, high computational power, if we finally understand how to really harness it. But that indeed is still in the future. 20 years in the future, I don't know, but we're not really quite there yet to fully harness the capabilities of the quantum computers. But let me pass on from this very conceptual introduction, and that's all I'll say by way of sort of scientific introduction to the basics of information processing with quantum mechanics. And I want to pass immediately on to the here and now. So what does a quantum computer look like in the year 2023? Well, actually, I'm showing you a few things that were published in Popular Science in the year 2022. At this level, it's not so different. Well, I'll mention one way in which it isn't different already. So you're often, I bet that most of you have seen a picture like this, and you are told this is a quantum computer. This is in fact a superconducting quantum computer. But I really have to, in a sense, disappoint you in saying, basically, nothing you see in this photo is functioning quantum mechanically. Nothing, there is not a qubit in sight in this picture. And in fact, this picture, this is courtesy of IBM, is just the control apparatus, or the physical structure that is built to house the quantum computer. I'll show you in a slide or two where the quantum computer is. It's actually out of view in this picture. And most of what you see here is the hardware that's needed to, first of all, make the device very cold. When this is in operation, there's a can over it. There's a thermal insulation can, so that the interior of this structure, in particular the lower regions, can get to extremely low temperatures, less than 1 Kelvin. And then there are many, many wires going from top to bottom, and those are the ways in which signals are brought in to control the quantum computer. But you do not, in fact, see anything about the quantum computer itself, the qubits, in this view. If you step out from this view, so here's the, this animation is showing a few things which I'll go through as it loops through. So a quantum computer is one where you have to issue instructions to it, which are turned into actual waveforms, which were shown briefly in that little part of the picture. And the picture that I showed a moment ago was on the right. Now it's just disappeared again. But I'm sure some of these you know quite well. That is, you, on a regular computer, you write a set of instructions for the quantum computer, which look like just regular instructions of a regular programming language. There it is, like QC measure. It goes through some magic box, which is the dark blue part of this picture, gets turned into very precise waveforms. It's shown as these sinusoidal pictures as you see this looping by, but in fact, they're much more complex than that. They're usually highly tailored to do a specific job, to cause a particular operation, like a measure operation, to occur. And then a signal comes back out, which is in fact the answer to the question, at this moment, is the qubit a 0 or a 1? And then you do that innumerable additional times. You know, if you're in the future, when we run, say, a factoring algorithm, there will be like 10 to the 18th such individual steps. At the moment, there are not nearly so many, but there are a multitude of steps. I want to say something about this dark blue region, that is the sort of the region where the computer instructions get turned into waveforms. These are highly important and specialized parts of this device, and they're probably the part which is kept the most secret by the companies that are doing this. So this is IBM's very fuzzy picture of the large control rack that is needed to prepare the signals that are going to go into the quantum computer. These are all electronic devices. They're regular digital or analog, actually mixture of both devices. And there are many, many channels, basically because every qubit has to get its own channel to the outside world. It is a little different in other realizations of quantum computers in that in many of the others, there will be some optics involved, so that computer instructions, that is regular CASM instructions, or some, Qiskit instructions will, from the high-level language, will be turned into optical pulses. That is not the case in this style of computer, which operates only on electrical pulses. Okay, so let me say a few more words about this computer. So finally, we pan the camera down to near the bottom, and now many, many more cables and control apparatuses and cables into these plugs. And the quantum computer is finally in this tiny little white region in the middle. So I didn't mean to advance quite so soon, but this is itself, and this is a chip, a region where the chip is mounted, where a chip is mounted. Let me just see if I can, I'm going to, on the fly, turn myself into a laser pointer. Maybe this one. Okay, so, oh, that didn't work. Never mind. Anyway, so the quantum computer is just this little region, and all this work is involved in contacting to it and sending very precise information to it, and then receiving precise information out from it. Now, a view of the chip as of 5 years ago, more than 5, maybe 7 years ago, at the beginning of the IBM cloud era, was that it looked something like this. Now, I'm not going to explain extremely much about what's on this chip. It looks like a microelectronics chip, but there are some important differences. One is that the device is way less miniaturized than a regular computer chip. That is, the working devices, the actual qubits, there are 16 of them on this, are in these little square regions, 8 of them lined up along here, and 8 of them lined up along here. And they are not so small. They're nearly 1 millimeter across. There is a working part. These are based on the physics of superconductivity. There is a very small working part, which involves the tunneling of superconducting electrons from one region to another. But it is fair to say that the entire structure, this entire millimeter size structure, is functioning as a qubit. Okay, so let me explain just a few more things about what has happened in the meantime to this in the years that it's been available. And I shouldn't overemphasize IBM here. I've used to work for IBM, but that's 13 years ago. And I admire their work, but I also admire the work of the Google company. I admire academic work at ETH in Zurich, for example. I admire, however, the ion trap work of Quantinuum, but I should be careful because I would have to now name about 12 more to be fair. So instead, I'll be unfair and just stop there, but just to emphasize that there are many organizations that have done things of this complexity and definitely higher at this point. All of them have this situation that there's a very considerable classical infrastructure that's needed to take care of their quantum computer. And then there's always some unique central region where actual qubits live and are very carefully shepherded through their operations. So let me say, however, a few things more about where this goes. What is the idea? The idea, of course, is to have more qubits. There was an insight, and this is already 20 years old, that more or less regular arrays, but square arrays, that is, I should say, two-dimensional arrays of qubits, are actually quite powerful as an architecture for a quantum computer. That's partly because it's well adapted to the needs of quantum error correction. Sorry, this slide has too many words on it. I was not going to say most of these words, but just to say that already, now almost 15 years ago, at a cartoon level, it was sort of understood where this was going. In this cartoon, it was understood there should be some kind of qubits. It was not even specified which. The green dots in some kind of regular two-dimensional array. They need to have things that couple them to each other, and it was understood that linear resonators are a good scheme for coupling them. So that's all these sort of gray bars are things that couple nearby qubits to each other. They also need electrical structures specific to read out the qubits. That's these sort of wiggly, squiggly structures, also like you saw on the chip picture. But most scary from the point of view of those who build quantum computers is that every one of these yellow squares indicates a place where information should flow in and out from the outside world. So in this concept, basically, each qubit should have two inflow or outflow locations. And that sets a scale for the working quantum computer. Now, as I said, these inputs and outputs, they can be optical, using optical fibers, let's say, or they can be electrical cables, but they have to be something. And they have to be something very carefully engineered, very precisely engineered, with low noise in mind, with very low temperatures, very precise control. Now, where this is going, IBM says that they have indeed proceeded along over the years, and they now foresee that they could go far beyond 1,000 qubits. That's what this last but very indefinite milestone for the current years, the next few years, is that they say possibly, they say 1K, meaning beyond 1K, beyond 1,000, but also maybe up to 1M, meaning 1 million and plus beyond qubits. And they have some concept for how to do that, but well, it's rather unclear how much of that they will do in the next couple of years. But just to give you a perspective of what they've done and what other organizations have done as well, but they've been very open about it. So I think this is worth, praising. That this is about 5 years worth of advances in their chips. They 5 years ago, they had a chip called Falcon, which now I don't remember the count of it, but you see it in the lower right here that that's something like 20 some qubits in this, according to the connectivity shown here. The year after that, they had Hummingbird, twice as big, the yellow patch here. The year after that, they had Eagle, another factor of 2 or more, actually, I guess in numbers of qubits, perhaps a factor of 4. And then the following year, they had Osprey. And now this year, as of now, they have Condor. So almost 1,000 qubits. That is the entire, background of this is the size quantum computer, the gate array quantum computer that they have now in their laboratories. Now, I understand their next step will be backwards. That is, these are impressive in the numbers of qubits they have. They're not super impressive in the quality of operations, the thing we call fidelity. And so they're going back to the drawing board and going back to smaller structures, but ones which achieve new fidelity goals, which make it possible to run longer algorithms, but also more exciting, perhaps for people like me, that makes it possible for digital error correction to start becoming effective for these quantum computers. And we have always felt, and well, always for the last 20 years, have felt that that is the way that finally we will get to really scalable quantum computing, is to achieve the conditions where error correction is possible. And I'd say we're getting close, but puts heavy demands on every aspect of the system to make it work extremely precisely, actually as an analog device, in order that finally digital error correction can be effectively used to make quantum computers do algorithms of essentially arbitrary depth or length, if you will, numbers of gates. Okay, so let me now step into my sort of historic mode. I started very generally, and now I talked about what's the present. Where did this all come from? So as I hinted at the beginning, I would say there were really multiple starts. Well, what everyone always says is that it started here. So here's a paper, actually it's more or less the transcript of a lecture given by Richard Feynman. Lecture was in 1981, but the published paper is 1982. And sure enough, this lecture has indeed many speculations or thoughts about the possibility of a quantum computer. So one can certainly point to this and say, yes, this is where the story got started. And I will definitely acknowledge that Feynman, this was an important impetus to the field, and rewards rereading. I recommend this as very interesting reading to those of you who wish to understand the basics of this subject. But I will say that this was, first of all, not actually the beginning. Here are some important long ago workers. And so I said, for example, that for me personally, the timeline begins with 1960, and this begins with Landauer, who understood some very basic things about information carriers, and in particular, how they would or would not consume energy. And it was his insights that told us that maybe we don't need a dissipative device to do computing. What I also focus here, or mention here, are the very notable contributions of scientists in the Soviet Union, and more particularly of the work of Yuri Manin. And those of you who are Russian-speaking could find some real surprise in the text that I have partially shown here. If you really want to have the page, I can send it to you. But who articulate several years before Feynman quite clearly what the point is of quantum computing. The large vector space, the possibility of controlling wave functions in that vector space. He actually had quite a cogent, abstract, but definitely cogent idea of what a quantum computer would mean. So now this work was little known outside the Russian-speaking world, but well, now we can see that if you really want to point to originators, that maybe one should point to Manin. On the other hand, the growth of quantum computing was not all that fast after Feynman's lecture either. That he himself did a little bit further work, and well, I just show a line of mathematics here to indicate that yes, he didn't merely speculate. He wrote down a few theories for what a quantum computer might be like, and those have been important. They were not revolutionary. He actually rather missed the point that quantum superposition was the essential aspect of quantum computing, so he really failed to notice that. But he did introduce ideas that led, on the one hand, to new ideas for the so-called complexity theory of quantum computing, and I definitely credit Aharonov for carrying this forward, in conjunction also with Kitaev, who had many other insights into what a quantum computer could mean. But this was only many years later. That is, Feynman unfortunately passed away in the late 80s, so his last writings in this were in the mid-80s, and it was in fact many, many years until these ideas came up again and came to the fore. Now, so indeed, I would say it took about, well, on my timeline, about 12 more years before really exciting things started to happen. And so I'll jump in my timeline up to this year, 1995. And at this point, in my view, things were really happening. That is, if you ask me, when did quantum computing start? It was right around this time, because this is where the rather abstract ideas of Feynman, or well, Manin perhaps, got turned into a set of concrete and very exciting ideas. This was among the first international conferences that took place, gatherings of people who were really primarily concerned with quantum computing, and some really exciting results were discussed at this meeting. I was there. There's the young me, but the factoring algorithm of Shor had just been discovered. And of course, I'm pointing to Shor in this picture. He's rather dim in this little side panel. But the discussion of his algorithm was certainly a large part of this meeting. But I've already mentioned the contributions of Dorit Aharonov and the beginnings of quantum complexity theory. There was Seth Lloyd, who was already speculating about using spins to make a quantum computer. I can point to, except I keep losing my pointer, here it is. There's Barbara Terhal, who introduced the thing called an entanglement witness right around that time. I dropped down to here. This is Tommaso Toffoli. Toffoli, you know, the Toffoli gate of quantum algorithms. Was introduced by him, and many of the co-authors, I don't know how many, but I didn't count, but there's Bennett, there's Joseph, the originators of quantum teleportation. So the, among the foundational concepts of quantum communication was very much discussed. I think I see 2 or 3 more of the 6 authors of that paper at this picture. So this was indeed one of the high point academic research conferences of my entire career. And, many, many exciting concepts were launched at this meeting that kept us busy for many years. Now, actually, rather absent from this were people who really knew how to build quantum computers, I would say. But still, there was very much speculation at that time. And I'll take you through a few of the considerations of what was going on. That is, I would say initially mostly from theorists. There were actually now many ideas. I mentioned Seth Lloyd, but in fact, there were many other ideas that all came to the fore within a few years. And I don't think I'll read through all of these. They include things that remain very active to this day as subjects for quantum computers, ion traps, neutral atoms, nitrogen vacancy centers, small Josephson junction devices, so superconducting devices like what I was featuring, and spins. But some of these also look not so familiar. The electrons on liquid helium has not taken flight, definitely. And let me also comment on nuclear magnetic resonance, that it leads the list, actually, because I'd say for quirky reasons, or I don't know, not absolutely the best scientific reasons, this was indeed the method that took flight very quickly, that some members of the group that I just showed you got very interested in this and felt that they could go into the laboratory and do work quite quickly to do quantum computing on the nuclear spins of molecules like this. Now, actually, the factoring of 15 came a few years later, but not many years later, on this precise molecule. And so that was, viewed as an important achievement. And there was a lot of attention to this. They said, oh, a simple instrument, you just make a sample, you put it in there, you measure, you don't need a lot of cables, you just need the kind of readout system that normal magnetic resonance instruments have. And definitely these things taught a lot about how quantum computing would be done. But I can say that I was, at this stage, I'll think, this is the late 1990s, I was rather resistant. I felt that this was actually not a good start to quantum computing. Maybe the important phrase is the one that I state here, not scalable. There was really no good concept for how this would ultimately be scaled. There were practitioners that thought maybe there would be, and they probably also said, well, it's not so important. We're just at the beginnings of this. Let's just try to get where we can get and see what will be next. But I was not so confident that that was a good approach. On the other hand, we had the example, let's see, let me go back, let me skip something. We had the example of ion traps already in this work, or this is two subjects that were scientifically very active in that time, in the 80s and 90s, and then ultimately were awarded the Nobel Prize in 2012. But they were indeed about controlling qubits in our current language. That is, in one case, controlling which energy level a beryllium ion would be in, what electronic energy level when held in a trap, or alternatively, what energy level of a Rydberg atom an atom would be in when controlled inside a cavity. So these were already known methods. And now you could say, well, were these the basis of scalable methods? In the form that they existed in the original experiments, no. But what influenced me very much was the fact that there had been actually a meeting in the preceding year. I had shown you the 1995 meeting, but there was even a meeting even smaller in 1994. And this, I would say, was the entire set of world researchers who cared in 1994 about quantum computing. It was definitely not a very large crowd. But I bring this out because this shows, in addition to some faces you would still recognize, a few that were not at the 1995 meeting, those being, if I can get my pointer to work, this is Peter Zoller and his colleague, even less visible here, Ignacio Cirac. Now, some of you know that Cirac and Zoller produced a very nice set of ideas of how and the ion trap as it existed in the year 1994 would actually work as a quantum computer. And in fact, they revealed these ideas exactly at this meeting in Torino, in Italy. And that definitely resonated with my thinking as, well, the magnetic resonance didn't resonate, so to speak, but their ideas for the ion trap definitely did. And it got me thinking almost immediately that, well, there must be something general to this. And I began some studies, first of all, of saying, well, surely we have to take a very broad view of what could quantum compute. And this is in fact my own first paper in quantum computing, and it had a table of possible entities that might quantum compute. And some of them, I would admit, are kind of weird and definitely not, not in play nowadays. The Mössbauer nucleus, definitely not. But other things like electrons in gallium arsenide, yes, became a pretty important thing, but also nuclear spins, also trapped ions, although indium turned out not to be the preferred trapped ions. I had my own sort of Gedanken apparatuses for what a quantum computer might be based on scanning force microscopy, which is better left sort of unsaid. But what I realized in doing this was that, well, yes, there is something really systematic behind this, or something actually fairly universal. And it was that within those years, and then in its final form, as I wrote them in the year 2000, were these criteria. Now, I don't feel, I'm not going to spend a lot of time talking about these. I wrote them up very carefully as a chapter in a book. And that's the version that you should all read if you wish to. However, this is cut directly from Wikipedia, and whoever made the Wikipedia page did a great job. In particular, they used, exactly my phrases for these, which I felt was important rather than paraphrases. But more importantly, you have a whole paragraph of descriptive text behind each of these criteria. Because these should be read carefully. I mean, the careful choices of words were made, and then I gave explanations for why. And then also sneakily said, well, look, the NMR quantum computer surely can't do this, that they really had no good way of initializing the state of qubits to a simple fiducial state. So to me, that was actually a killer for that. But I also acknowledge that the Sirac and Zoller approach to ion traps checked all 5 boxes. So they definitely had effectively thought through each of these 5 criteria and had answers to all of them. And so when I did subsequent work, for example, on quantum dots, I really tried to make sure that these would be satisfiable. And they weren't always in the ways expected. For example, there's the statement that, well, the decoherence times should be long-lived. And when Daniel Loss and I said, we think that electrons in gallium arsenide, their spins would be very long-lived and would be a good qubit, we missed part of the physics of the nuclear spins, the other nuclear spins in the gallium arsenide lattice. And that's caused years of work. And finally, electrons in gallium arsenide are not actually the preferred qubit, quantum dot qubit, largely because of criterion 3. But luckily, there's an alternative, and there's very active research currently on electrons in silicon or silicon germanium structures. All right, so I'm actually rather near the end, and indeed, I wanted to leave a lot of time for discussion. I want to acknowledge that there are many ways of writing criteria for quantum computers. I've been asked if they should be updated, and I said yes, but not necessarily by me, because they should and have gotten much more specific. That is, well, what are the criteria for a superconducting processor to work? Well, you have to get way more specific about, well, you have to do quantum gates, and they have to be universal, and they have to be very precise. That was sort of understood. That is, in the year 2000, when I said decoherence times, I also meant other things, contributing to the imprecision of qubits. And boy, there's a huge amount of knowledge and lore and things that have to be checked that make it possible to really satisfy the detailed requirements for that processor. And then for a photonic quantum computer, the requirements are completely different. That the ability to measure the qubit, to measure the state of a photon, is key and difficult, and definitely a problematic part of making an all photonic quantum computer. Let me move though to, I like to do honor to another thinker who I think, while he was not present at the early stages, well, in a sense was, because David Merman developed very original ideas about how you test for quantumness in the form of Bell inequalities or the violation of Bell inequalities. But he wrote a beautiful book about quantum computers, which in its body is a nice, excellent undergraduate textbook for teaching quantum computers to a broad set of students. But his first page has some very beautiful, observations, and I won't read them all to you, but maybe I can just feature one or two of the words here that, because it's in a sense the last sentence that encapsulates the real difficulty of making a quantum computer. In a quantum computer, the physical systems that encode the individual bits, quantum bits, you might say, must have no physical interactions whatever that are not under the complete control of the program. Now, in retrospect, this is a little too harsh. That is, if it were really true, no physical interactions whatever, then we could forget about it, that there's no such thing in physics as no interactions. But controlling them so that they're at a very, very low level, yes, true. And that is the extreme difficulty of making a quantum computer. I'll close with some just sort of aphorisms in some sense. I'll indeed say that, of course, we've turned the corner, but this was already a long time ago, that we don't anymore have gatherings, where there are 20 people and they're the only ones who care about quantum computers, that we've been filling vast auditoriums with quantum computing enthusiasts, but already almost for 20 years. But the sort of phase transition of that indeed occurred in this period from the late 90s to the early 2000s. But I mean, of course, nowadays you could fill a whole Congress hall with people interested in furthering the science and technology of quantum computers. Here are a few thoughts to leave you with. Bennett, who was the, in a sense, forefather of quantum communication in the form of quantum cryptography, also quantum communication, has really a theorem that says that computation does not actually require consumption of power. That's a beautiful insight, however, not confirmed or not borne out by our current use of power. I think this statistic of 2% electricity consumption is a bit out of date, actually, that our use of power, really electric power in running computers is quite huge, despite Bennett's theorem. And another thinker of that time, of some time back, Margolis, observed and had mathematical models that said quantum computers could operate autonomously. But actually they don't, and the ones that we know how to build are heavily under the control of external agents. And to me, it's understood that a working quantum computer has perhaps more than a passing resemblance to a detector at a particle lab. This is not by no means the biggest one that exists in the world. This is one that's, I guess, been decommissioned at Fermilab, but it also has a vast amount of basically classical electrical technology surrounding a quantum core. And that's kind of looking like what a quantum computer will continue to look like into the future. So anyway, thanks for your attention. And we've reached the time when we can have some discussion.
Thank you so much, David, for this magnificent presentation. I really love the comparison with the Fermilab detector at the end. There are already many questions, and everyone get ready to ask all your questions. This started when you showed the IBM design. There were questions, can we scale this up to 3D? Are there any considerations there?
3D, well, at one level, 3D is already happening, and it's in the sense that chip engineers mean it, that they use 3D structures, meaning they use multi-layer structures. And it is known that some of the for example, the first stage measurement apparatuses are best put on another chip. So they're put on a facing chip, facing the chip with the qubits. So that's a first step into 3D. Actually putting the qubits 3D is an interesting idea. And those of you who are looking very, very carefully at IBM's roadmap or have looked at it before, see a little cartoon that implies that they will stack up, but they'll imagine stacking up whole modules. So they'll make a whole rather big chip with 1,000 qubits, let's say, and then to have 1,000,000 qubits, they'll stack 1,000 of those. So they have to have some interconnects among them. My current expectation, it will not be truly 3D in the sense there won't be qubit to qubit entangling operations between these modules. That'll all go via the edges, and the quantum computer will still be in a certain logical sense, still basically two-dimensional. So, but it remains an open story. Actually, for neutral atom structures, there are maybe more realistic ideas of how you would really go to 3D and have actual 3D connectivity, which is understood to be good for error correction, potentially. Maybe I'll leave it at that, though.
And Miguel Gonzalez from Mexico asks, when you were at IBM and you were a theorist, but were there already plans back then to really build a quantum computer at IBM?
Yes, definitely. Well, it came in stages. IBM's work was purely theoretical until around the year 2000. And then the subject became sufficiently interesting, but it had to become sufficiently interesting to some IBM executives that they said, okay, now we would be welcoming if some of the experimentalists on staff would start thinking about this. And at that point, one experimentalist, really only one, who had experience in superconducting devices said, I'm going to try it. And he was encouraged to try it. And we teamed up. We were working together right from the beginning of that. I was starting to do modeling of superconducting devices, really motivated by his work. His name was Roger Koch. He tragically died suddenly in 2007 before IBM's program really got off the ground, but thereafter it really took off and became a very big experimental activity at IBM.
Some people point out that the conference at Torino really resembles the Solvay conference at 1927, if I remember well.
Okay, well, it's sort of approximately the same scale. It also involved, it occurred because of a private benefactor, as did the Solvay conferences. It had a lot of people interested in very basic quantum mechanics. I'm sure we can come up with many, many other differences, though.
Yeah, I'm sure too. Mohammad Reza from Iran asks, will there have to be updates on your criteria if more advanced algorithms, even more advanced than Shor's or Grover's, were to be discovered in the future?
I would say no. I think that, well, I'm not updating algorithms anymore. Sorry, I'm not updating criteria. I think that these criteria would have been definitely not so useful if the promise of adiabatic quantum computing had really flowered. Now that's still a going concern, but it's a very, very different approach to quantum computing, which Aharonov proved was in some sense, some formal sense, also universal for executing quantum computing. The trouble is it has very poor tolerance to fault. So that's why I don't believe that adiabatic quantum computers will ever be really scalable, full functioning quantum computers. Those would really take a different set of criteria because they're not based on the idea of running quantum gates. But merely the discovery of new gate-based algorithms, no, I think, my criteria just one's about how you build the machine, and the machine is supposed to be a universal machine, supposed to run any algorithm that's proposed within the setting of gate-based quantum algorithms.
Someone indeed also asked, how would we apply it to the D-wave quantum annealer? And
Yeah,
yeah, you just
well,
discussed.
okay, I think I've said pretty much all I would say about that. There's certainly some quantum power to the D-wave computer, but it's also a very noisy quantum computer. And I think the jury is out on how far we can go before we can really suppress noise. I mean, this is an active and controversial subject that it seems there's a bit of an arms race now that a new generation of quantum computers is fielded, and then algorithms are run on it, and then there's a statement, oh, now we're finally at a stage where this is not something that could have been computed on a regular computer. This happened 4 years ago or 3 years ago in the so-called Google quantum supremacy. It also happened 2 weeks ago in the IBM so-called quantum utility paper. And in both cases, groups from basically many-body physics came up and said, look, we have algorithms at our disposal that we can run on regular computers, and we can do these quite easily. So, you know, despite the fact that it was expected that it would take 10,000 years of running time to reproduce, but in fact, it only took a few days of running time. So we're, I think that arms race will keep going for a while, and may only be settled in the era of error correction, or it may be that just a regular, I'll say NISQ, I haven't used that phrase, noisy intermediate scale quantum algorithm, when run on a 1,000 qubit machine, will finally settle the issue, and there will not be an effective classical simulation of that, but we don't know.
Now a question to answer personally from Rupayan from India. What is your favorite qubit type and why?
Well, I've gone back and forth on that. I mean, I love spins in semiconductors, but that's partly because of my research orientation. I'm a solid state physicist, and I love crystal physics, and I love the intricacy of semiconductor physics and how it can be applied. Now, having said that, though, the spin qubits, quantum dot spin qubits, have not taken flight. It's really one big technical problem, which is making entangling gates that work between qubits that are not, that are at a sort of intermediate distance from each other. What I mean by that is, for example, a micrometer, because we have excellent entangling gates at the nanometer scale, but that's too close. And there's an architectural problem of how to spread the qubits out so that you can get all the control lines to them. There are great ideas for how that might be overcome, and over time, these qubits have continued to get better in the last 20 years. So the basic qubit is really good at this point, but that step is missing. Now, also, some days I say I love superconducting qubits because I've also been modeling them for years and years and years. So those are my favorites.
That is wonderful. And Maya from Iran also asked something related, which you, in my opinion, answered, because she said silicon-based quantum dots achieved a fidelity of 99%. What is the reason for superconducting platforms instead of quantum dot-based ones?
Well, there are two parts to that. One is that there is also a kind of arms race in fidelities. And I would say this is not a new message, but we understand that 99% fidelity is not the end point, is not actually good enough. Now, luckily, 100% is not necessary. That is, David Merman's comment was not true. That is, we don't need absolutely 100% perfect fidelity. But the experimentalists have recognized this, and they've been striving for, approaches that definitely go beyond 99%. And there are new results. Let's see if I can remember, if I can quote the number properly. 99.98, I think, is a number that one can quote, or 92. No, 99.92, I think, is a entangling fidelity that one can quote. And that's definitely way better than 99.0. I think that will become the standard. Now, how many nines do you need is a big question. And theory has said all along that about 3 nines is enough. But that's within the setting of fairly simple models. So we will see if it's enough. That is, it then gets tied up in all the sort of architectural questions of, can you really use to the full the fidelity that you've got, and you don't fumble it by doing some other thing wrong. And you should be able to do it all the time throughout an entire array of qubits. So we will see. And it gets to difficult experimental questions. I'll throw in one that these otherwise very beautiful superconducting qubits turn out to be susceptible sometimes to ionizing radiation. And so that causes the effect that most of the time they're 99.9%, but then an energetic particle hits them, which may happen only once a few minutes, and then it blasts it for, fidelity becomes very poor for a fraction of a second, and then it recovers again. And this has been very carefully investigated because some, kind of irreducible source of these are cosmic rays, are muons from cosmic rays. So people have done experiments deep under mountains to confirm that, yes, indeed, these are the source of some of the problems with coherence. But how do you precisely characterize something that's 99.9% almost all the time, except for, a few milliseconds out of a minute? This is sort of a new problem, but definitely a problem. So, but it's also a problem of how experimentalists communicate these results, because it's not captured just by the idea of fidelity. So you need good fidelity and better and more. And maybe we don't understand all the mores at the moment.
Let's look back a bit and also in the future. Ron from Chicago asks, some quantum professionals indicate that the current state of quantum hardware is akin to the vacuum tube state of classical computers. What are your thoughts? And Artem from Mexico asks, what is your vision for the distant future of the quantum industry?
Oh boy, okay. The first one's easier. Yes, I do kind of agree with that. I remember being quite struck in reading the biography of Turing, but you should look not at the famous part of Turing's career when he was cracking codes, but the years immediately after, when he actually became a private or a researcher at a university, Manchester, was it? But the point was that he joined a group that received among the first digital computers, but which was definitely a vacuum tube model. And he did definitely useful work with that. He made models of, how leopards get their spots and other sort of biological pattern problems by, running simulations. But his hardware was very shaky, and there are stories about him having to go into the basement, sort of kicking the machine, like to the magnetic drum, which hold, the memory drum would be a little bit defective, and he'd have to, kick it to make sure it was spinning properly. So, we're a bit in that stage where the basic hardware is just barely working well enough and definitely needs a lot of kicks. I'm told stories by people who use the cloud machine that, it's recalibrated regularly, I think more often than once a day, but that you really want to have the luck of having your run occur right after a calibration and not after a few hours, because then your results are definitely worse. That the machine is drifting and getting successively worse in a noticeable way. So maybe that's that. Now the other cosmic question was the far future. I don't know. I mean, I think any of you can have just as good an idea about that as myself. I was intrigued by hearing that people are thinking of putting data centers on the moon. So I think that putting a quantum computer on the moon would be a great long-term project. I then learned that people say that this data center, that we could do it, or we will do it very soon, because the first data center on the moon will be just a sort of like a terabyte disk that you just drop on the surface and make sure that it can communicate with Earth, and then, aha, there's a data center, a rather modest data center.
I think we should keep collaborating on that all together with all the input from different backgrounds from the group. There are still really many questions. We will pick a couple more. And for everyone, there will be upcoming hardware lectures on the different qubit modalities and also on their architectures. So then we can continue the discussion on those. Carolite from Cameroon asks, do you think that we will discover a new material in the future that will change everything, as silicon did for the implementation of classical computers?
Always possible. I mean, maybe I should say yes, because the field of materials is so gigantic and the number of possible combinations is so large that I'm sure there will be such things. But planning breakthroughs in materials is notoriously, well, impossible. And it seems the right prescription for materials is you just make sure there are experts around who are constantly mixing up new stuff, and you just keep watching what they make, and maybe encourage them to throw in things that are magnetic or things that are have a lot of hydrogen or something like that, some very broad guidelines, and just see what they manage to make. Definitely, like the current development of room temperature superconductors is a fundamentally materials thing, which has to do with the insight that you can make crystals that are almost all hydrogen with a little bit of other stuff. And that's an interesting combination for making really a new class of materials, totally unrelated to quantum computers. But, well, you have to allow a lot of freedom in that kind of research.
And like that, indeed, new materials define human eras. Let's see what is next. Yash from India really wants to know more about the qubit architectures. Why is Google's Sycamore or IBM's Osprey modeled the way they are? What is the physics behind qubit connectivities? Could you comment a bit on that, and it will discuss more in
well, that's a whole course worth of information. Just to touch on one or two thoughts. IBM and Google made quite different decisions about what their chips how their chips would function. Sycamore versus Osprey is a good example. Sycamore has what are called tunable couplers, which means that there's even extra control signals that don't go to the qubit, but go to the couplers between the qubits, and in a fairly explicit way turns it on and off. IBM chose not to do that, and they get all their turning on and off of entanglement by what signals are sent to the qubits themselves. In both cases, the couplers are electrical structures. They're typically, they exploit the physics, the electromagnetics of guided waves, and use the quantum mechanical properties of guided waves in resonator structures to couple qubits. That's enough of that lecture.
Perfect. And indeed, everyone, keep your questions ready for the virtual lab tours and hardware lectures there. Priyal from India also really wants to know more which technologies you really think have the potential to gear up the future of quantum computing. You already mentioned a couple of things.
Well, I think the only one that I showed you a big list, and I said many of them are in play. Maybe the one that fell out of contention and then came back are neutral atoms. I think that's an interesting coming subject that maybe 5 years ago would have said, oh, kind of interesting idea, but it's not working. And then now it's working. And, by the usual standards, the high fidelity and many qubits and a lot of, good control. And so we see several organizations now launching, order 100 qubit devices, either simulators, but also universal computers, quantum computers. So that's an interesting kind of new arrival, but not really so new. That is, we knew 25 years ago that there's good physics there that could be exploited. For the rest, it's just, keep watching the silicon, the germanium, the calcium ions, the ytterbium ions, the transmons, the other varieties of superconducting devices. I think the quantum computers will come from somewhere on that short list.
We will see it all the next coming years and decades. Taha Ruaba from Algeria, a quantum expert at Constantine Quantum Technologies, asks, what is your opinion about the recent developments at Google, Continuum, Microsoft in topological quantum computing?
Okay. One should make a distinction. There are topological ideas for quantum computing that are purely software, you might say, that are very tied up in how we define error correction codes. And some of the work that you hear about is indeed the realization of error correction codes based on topological principles. I mentioned Aharonov and Kitaev. Actually, it was mainly Kitaev's work that first set that in motion. Now, when you talk about Microsoft, though, they put a bet on a rather different approach, which is to build or use topology to build the qubit itself, as part of the really fundamental constitution of the qubit. And that's in the form of, well, we would say abelian or non-abelian anyons, or you might say the catchphrase is Majorana zero modes. This has had a rocky history in the last 10 years. There are beautiful ideas for how that would work. Requires quite exotic materials combinations, which Microsoft has worked hard on, and other researchers. But the sad state of affairs is that after 10 years of research, there's no qubit. So it fails to come to criterion 1. And until that's achieved, it's hard to say much more about what could be done. I mean, there are advocates, and definitely advocates within Microsoft, that say, when we have this as a qubit, it will have fantastic fidelity right off the bat. And so we'll leap over all these other approaches immediately. I say maybe, but until we have the qubit, there's no way of saying. And there are also plenty of studies that say, well, if you really look carefully at the, what might come, it might still have sources of noise that we have not really understood. So I'm not so optimistic about that approach.
We will finish with 2 questions with very quick answers. What is the quantum application that you are most excited about to see in future? That you expect there will
factoring.
be.
Factoring, pure mathematics, pure mathematics.
And then a futuristic question. Do you think quantum computers will be the end of progression in computing? Will there be anything above that?
Yes and no. I don't think there will be any further physical basis for computing, but I'm certain that the nature of computing will nevertheless continue to evolve in fundamental ways.
David, thank you very much for this fantastic talk. It was really an honor and pleasure to have you. Thank you for this great session.
Okay, dank u wel, Marlou.
Even in Dutch. Bedankt, David. Geweldig en een hele fijne avond. It was a great pleasure.
Voor jou ook. Okay. Yeah, thank you all for listening.
Oh, thank you very much. This was also by far the most questions. I know many questions have not been asked, but for some of them, we can relay them to the next days where we can dive in depth for the hardware panel, the hardware discussions. Really looking forward to that with all of you. And David just mentioned one of the qubit modalities that really ramped up the past 5 years. And that is the topic we will discuss now with Jeff Thompson from Princeton, namely neutral atom quantum computing. So thank you, David, for also paving that way. And I would like to thank you once more for this great lecture and wonderful Q&A session.